Space, the final frontier. But humanity's reach for the stars has also yielded technologies that impact our lives here on Earth. Ballistic missiles are one such example. These rockets, capable of carrying payloads across vast distances, are a cornerstone of many nations' defense strategies. But how much do we really understand about these complex machines? Ballistic missiles represent a pinnacle of engineering and scientific achievement. Understanding their mechanics and history is crucial to comprehending the geopolitical landscape we inhabit. Let's embark on a journey to demystify these fascinating and formidable creations. Join me as we delve into the world of ballistic missiles, exploring their mechanics, their evolution, and their impact on our world today. Imagine throwing a ball into the air. It follows a curved path, governed by gravity and its initial velocity. Ballistic missiles operate on a similar principle, albeit on a much grander scale. The flight of a ballistic missile can be broken down into three phases: boost, mid-course, and terminal. During boost, powerful engines ignite, propelling the missile upwards. This phase is crucial, setting the stage for the rest of the journey. As the missile ascends, it gains altitude and speed. Once the engines exhaust their fuel, the missile enters the mid-course phase. Just like the ball we tossed, the missile is no longer being propelled. It coasts through the vacuum of space, its trajectory determined by the laws of physics. Gravity pulls it downwards, while its initial velocity carries it forward. Finally, the missile begins its descent, entering the terminal phase. These warheads then plummet back towards Earth at incredible speeds, guided by sophisticated systems to their intended targets. Not all ballistic missiles are created equal. They come in different sizes and capabilities, each tailored to specific strategic needs. One key distinction lies in their range, which determines the distance they can travel and the potential targets they can reach. The most commonly used classification system categorizes ballistic missiles into 4 groups based on their range. First, short-range ballistic missiles, or SRBMs. These missiles, with ranges typically under 1,000 kilometers, are designed for tactical use on the battlefield. Their shorter range makes them suitable for targeting enemy formations, military installations, or infrastructure within a limited geographic area. Next, we have medium-range ballistic missiles, or MRBMs. Covering distances between 1,000 and 3,000 kilometers, MRBMs extend the reach of military forces, allowing them to strike targets further afield. They can be used to target strategic assets in neighboring countries or regions. Then there are intermediate-range ballistic missiles, or IRBMs. With ranges between 3,000 and 5,500 kilometers, IRBMs bridge the gap between regional and intercontinental capabilities. Lastly, Intercontinental Ballistic Missiles, or ICBMs. These behemoths, capable of traveling over 5,500 kilometers, represent the pinnacle of ballistic missile technology. Understanding these nuances is crucial for accurately assessing the potential threat posed by different ballistic missile systems. Launching a missile on a parabolic arc is only half the battle. Ensuring it reaches its intended target thousands of kilometers away requires sophisticated navigation and targeting systems. These systems act as the missile's brain, guiding it with incredible precision. Early ballistic missiles relied on simple inertial navigation systems, or INS. These systems use gyroscopes and accelerometers to measure the missile's movements and calculate its position relative to its starting point. While effective over short distances, INS accuracy degrades over time, making it less suitable for longer-range missiles. To improve accuracy, modern ballistic missiles incorporate a variety of advanced technologies. These include star trackers. These sensors determine the missile's orientation by locking onto the positions of known stars. GPS, or Global Positioning System. By receiving signals from a constellation of satellites, GPS provides highly accurate location data, allowing for precise course corrections. TERCOM, or Terrain Contour. Matching. This system compares the terrain below the missile with pre-mapped data, making adjustments to maintain the intended flight path. These advanced navigation and targeting systems have significantly enhanced the accuracy and effectiveness of ballistic missiles, making them formidable weapons systems. At the heart of every ballistic missile lies its propulsion system, the powerful engine that propels it towards its target. Understanding the principles of rocket science is essential to grasping how these incredible machines achieve their incredible speeds and altitudes. Ballistic missiles typically employ multi-stage rockets. meaning they consist of 2 or more rocket engines stacked on top of each other. This design allows the missile to shed unnecessary weight as it ascends, improving efficiency. Each rocket stage contains its own fuel and oxidizer, the 2 key ingredients needed for combustion. The most common fuel types are liquid propellants, such as kerosene and liquid oxygen, or solid propellants, which resemble a hard, rubbery material. When ignited, the fuel and oxidizer mix and burn inside the rocket engine's combustion chamber. The development of more powerful and efficient rocket engines has been a key driver of ballistic missile technology. The history of ballistic missiles is a fascinating journey through technological innovation and geopolitical rivalry. It all began in the 1930s and 1940s with the development of the V-2 rocket in Germany. The V-2, short for Vergeltungswaffe 2, Retaliation Weapon 2, was the world's first ballistic missile. Designed by Wernher von Braun and his team of engineers, the V-2 was a technological marvel for its time. It was powered by a liquid-fueled rocket engine and guided by a simple autopilot system. During World War II, Germany launched thousands of V-2 rockets against England and Belgium, marking the first use of ballistic missiles in warfare. After the war, the United States and the Soviet Union raced to acquire the V-2 technology and the expertise of German scientists like Wernher von Braun. This marked the beginning of the Cold War arms race, a period of intense competition between the 2 superpowers to develop increasingly powerful and sophisticated ballistic missiles. Over the decades, ballistic missile technology advanced rapidly. Today, ballistic missiles remain a key component of many nations' defense strategies. In an age where technological advancements continue to reshape the world around us, understanding the tools that shape global security is more important than ever. Ballistic missiles, with their immense power and global reach, are not just weapons. They are symbols of human ingenuity, ambition, and the enduring quest for strategic advantage. By delving into the science behind ballistic missiles, we gain a deeper appreciation for their capabilities and limitations. Understanding their propulsion systems, guidance mechanisms, and the devastating power they can unleash allows us to engage in informed discussions about arms control, deterrence, and the future of warfare. Equally important is recognizing the historical context that shaped the development and proliferation of these weapons. The Cold War arms race spurred remarkable advancements in rocket science, materials science, and computer technology. Advancements that have had far-reaching impacts on fields ranging from space exploration to telecommunications. As we look to the future, the challenges posed by ballistic missiles will likely persist. By fostering a greater understanding of ballistic missiles, their history, and their impact on our world, we empower ourselves to make informed decisions and work towards a safer and more secure future for all.